Okay, well, we'll get started. First of all, before we get into the seminar, I wanted to acknowledge that today we're meeting on Turrbal and Yagara country and acknowledge the traditional owners of that land, and acknowledge their elders, both past and present and future leaders of those peoples. And also what I wanted to acknowledge, given that we're talking about mangroves, is the Quandamooka people who have cared for mangrove country and sea country around Moreton Bay for tens of thousands of years. So yeah, that's what I wanted to say there. And what I also wanted to do is introduce our speaker for today, Alvise Dabala, who has a master's from the Tropo Mundo program, and has also worked at iAtlantic. So he brings kind of a very big background in spatial prioritization to his PhD here at the University of Queensland, where he's working with Anthony Richardson and Daniel Duck. So today he's going to talk about optimizing mangrove conservation across the globe. So thanks very much, Alvise.
Thank you. Okay, so today I will talk about two of my projects. One is the one that I did during my master, trying to maximize ecosystem services while protecting mangroves biodiversity at global scale. And the new one is my first chapter of my PhD, which is about climate smart conservation planning for mangroves. So,
Try now.
Okay, so mangroves are really important ecosystems for biodiversity. We have multiple species that live in mangroves, both from the marine side and also on the terrestrial side. But also, mangroves provide a wide array of ecosystem services for people. For example, mangroves sequester a lot of carbon, both in their biomass and also in soil. Mangroves are also providing a lot of benefits to fisheries, as they are important nursery areas. So many crustacean, mollusks, fish grow in mangroves, then maybe they migrate to coral reefs, seagrasses. And but also they protect the coastline from surges, floodings, and so they protect coastal populations. And they also have many other values, like cultural values, and many others. However, mangroves are threatened by both anthropogenic threats, like the conversion to aquaculture and agriculture, or non-productive conversions, and also urban development, but also they are threatened also by climate change, especially we can observe coastal squeeze when there's like sea level rise and the presence of human barriers block the movement of mangroves landwards in response to sea level rise, or also by intensification of cyclones that are predicted in the future, or droughts. So with area-based conservation tools, we can try to protect mangrove areas from clearing and also try to maintain the ecosystem services. However, the idea of our studies were to try to see how we can select areas that are providing the most ecosystem services, and also how we could include climate change when we develop network of area-based solutions. So, and this is in the framework of systematic conservation planning. That is a stepwise approach for mapping conservation area networks that then can be implemented. And especially we look into spatial prioritization. So the selection of the priority areas that we want to conserve based on multiple goals and objectives. And to develop spatial prioritizations, there's multiple tools. And for example, SNOW is from Marxan, zonation, but the one we're using is prioritizing. So when we do develop a spatial prioritizations, what do we need? We need some features so that are the distribution of different biodiversity, like for example, certain species where they are distributed, or certain geomorphic features. If it's open ocean, where are the hydrothermal vents, or other kind of features. And then for each of these features, we need some conservation targets. That is the amount of each of those features that we want to be protected in a finite network of protected areas, and then a cost. How much it will cost to implement that network, how much it will cost to select a certain area and include that in a finite network of protected areas. So in this case, in our two studies, now I will present mainly the layers that where we use, and then maybe I will do a bit more in the details of the methods later on. However, we used the global distribution of mangroves from the Global Mangrove Watch, and then some data on mangroves biodiversity, especially the IUCN Red List mangrove species distribution, the mangroves by physical typology working out, and marine provinces for the first studies. But then for the second one, we changed, instead of using marine provinces, we used country to see the difference between a global scale and a local scale conservation plan. So the Global Mangrove Watch report, based on satellite images, the distribution of global mangroves, also recorded gains and loss in the years, and yeah, it's quite precise. For the first studies, we were using the previous version that was missing some areas, like for example, around India, there were many mangroves that were missing, and now we're using the new version for the climate smart study. Then we are using IUCN Red List mangrove species, and we're including 67 species of mangroves, I think, and because the distributions are so broad, we then try to intersect them with the Global Mangrove Watch distributions to have a more precise distribution of species. And then mangroves by physical typology differentiate between deltaic, estuarine, lacuna, coast, and we are trying to intersect the species distribution with these data to increase replication and representativity across different habitats. So yeah, now I'm talking about the first study, what I did during my master's thesis, together with Daniel and many others. And that was, we called priority areas to protect mangroves and try to maximize ecosystem services. So when we develop spatial prioritization, usually we try to protect biodiversity and meet conservation goals we have, while minimizing the conflicts with the economic activities. However, we don't really consider most of the time the ecosystem services that these ecosystems are providing. So what we did was we started from the global mangroves distribution of 2016. We overlapped it with planning units that divide the distribution in multiple areas that can be selected or not. And then we overlapped it with these biodiversity features, so the species that were divided by geomorphic and sedimentary setting, and then also by marine provinces. And then with some ecosystem services, we focused on the value of the properties that were protected by mangrove, and the number of people protected, the carbon stored by those mangroves, and the fishing intensity in those areas. And at the end, we also overlapped the protected areas network. So for this spatial prioritization, what we were doing, we were setting some conservation targets. So each species has a different target. And then we were setting a budget for the amount of area that could have been selected. So we were starting from 1% of the total area of mangroves, reaching 100%, and so increasing of 1% each time. And so every time we were running the prioritization, the algorithm was trying to select the areas that were minimizing the shortfall between the amount of area that we were selecting in blue and the target in red. And also we were including the ecosystem services as a feature, and the target for all those was set as 100%. So every time trying to minimize the shortfall, the algorithm was trying to maximize the ecosystem services provision. So what we wanted to do was trying to identify those areas that, if efficiently protected, could ensure the conservation of mangrove biodiversity and of the most ecosystem services while selecting the smallest area possible. That's why we're using the area as a cost. So this is the kind of map we were having as a result. This is aggregated, like the planning units were much smaller. But yeah, it was impossible to see when it's not aggregating them like this. And the rank shows like how when the selection was done. So those that were selecting first were those that we define as higher priority. So those with 1, and then going to the yellow color, we have those that were lower priority. Way. And in the radar plot there, we show the percentage of the total value of the ecosystem services that we were reaching for like 10%, 30%, and then 50% of the selection of the total mangrove area, and also the amount of biodiversity target that we were reaching. And yes, and then another questions that we had was like, we wanted to assess how well the current protected area network represent the mangroves biodiversity and ecosystem services. So we looked at this most strict protection, so IUCN 1 to 4, and we found that around 13.5% of the local mangroves are really protected. However, only 4.5 of the areas that we identified as high priority, so the top 10%, were protected by this network. So actually, the protection is worse than random. Like we would have expected at least 13.5, but we're just seeing much less of those areas as protected. And we wanted to select the smallest areas possible, as I said. And so we see here, we have the percentage of those conservation targets that we reached. So we have a target for each mangrove species split by the various other layers. And then we were trying, this is the area budget, no? So we started from 0% and we increased to 100. Here we started, we were expanding from the current protected area network. So we started from 13.5%. And we see in dark blue, the result we have when we only include biodiversity, when we are not considering system services, and in light blue, that the result we have when we also include ecosystem services. And we see that the results are really, really similar. So it means that at the end, we don't really need a much bigger increase in the area to include those ecosystem services. And here we see how well we are including those ecosystem services when we are considering them. And we can see that the curve for most of them, it's almost logarithmic. It could be like we had results where the curve becomes much better, but we need to increase the weight of ecosystem services. So the cost for including ecosystem services becomes much higher. We need a much larger area. And we see it does quite well for properties and people, also for fishing. And for carbon, it's almost linear, but that's because the distribution of carbon benefits, it's less dissimilar. For people and properties, we had some areas that were at really high values, while for carbon, the distribution is more equal in different areas. And then we wanted to identify the priority areas that could be considered for expanding the current marine protected area network. And we found that most of the opportunities were in Asia and Oceania. However, that's what we probably could have expected, because that's where we find most of the total mangrove areas. There's a high species richness. We have most of the mangrove species there. The production is quite low in most areas, and there's a large amount of ecosystem services provisioned in this area. So what are our main findings? We found that most of the high priority areas that we identified are not currently protected. That then there is, in this case, there's some opportunities for optimizing future protection, trying to incorporate ecosystem services provisioning. That some of the proposed protection is close to urban area, and that could make it difficult to manage those areas because of the human pressure. However, the cost of the enhanced management of those systems can be mitigated by all the benefits that mangroves are providing. And yeah, now I'm moving to what I'm doing now. So this climate smart conservation plan for mangroves that we found is could be marginally costlier than one that is ignoring climate change. So yeah, going back to the same graph, here I'm saying that we should also think about climate change. There's many areas of systematic conservation planning, I think, that sometimes we are not considering, and it's difficult sometimes also to consider altogether. But yeah, climate change is particularly important for mangroves because we say they're threatened by multiple climate-related pressures. And so we included a climate change layer, and in particular is something that Christina Bulow and other people are working on, and it's a forecast of mangroves net loss or gain in the future based on a network model that include climate-related pressures and also some anthropogenic pressures. So here I'm showing some of the layers, and in particular, they divided between the seaward edge of mangroves and the landward edge because they reply in different ways to the different pressures. And here we see in light blue, the probability of expansion of mangroves. So like in the blue areas, the prediction is that mangroves will expand their area. And in red, orange, it's those areas where we are expecting mangroves to be lost. And yeah, we see, and then the size corresponds to a gradient to high probability of gain to high probability of loss. Yes, so these are some of the data we are including. And also to include those data, we are not anymore using the same methods we were using before. But what we are trying to do is trying to reach all the conservation targets we set at the minimum cost. So in this case, we just have one result. It's not multiple prioritization. We are running one after the other. And to include this climate-related data, we are using a method that Tim developed, and that is called like climate priority area. And what it does is like we split the distribution of the feature in two. And one is the climate priority area, for that is the areas of higher climate resilience in this case. And we assign a target of 100% for this part of the distribution. And then for the rest of the distribution, we just leave the algorithm free to select any mangroves not considering climate change. And yeah, we try to run this for multiple thresholds. So we start from like 5% of the target that we want to reach for each feature, and then we go to 30% to see how much it changed, increasing how much climate smart is the final result. Okay, so this is one of the results we have. So what I was running was a prioritization without including climate change and one including climate change. And in light blue, we see those areas that are selected by the climate smart prioritization, but not by the climate naive, so the one that is not considering climate change. In red, those that are selected by the climate naive, but not by the climate smart. And in yellow, those areas that are or not selected by both or selected. And obviously, there's like gradient. And yeah, and also in this case, the flying units were smaller, but then they had to aggregate them to make it visible. So yeah, we wanted to see how much larger is a climate smart marine protected area network than a climate naive approach, where they meet the same biodiversity objectives. So we had the same target for biodiversity, and we wanted to see how much more costly it is to climate smart, make it climate smart. So here we say that we are able to make the network more climate smart. We see that the resilience of the network, the mean resilience, is moved on the right side, and we on the value of 100, we have those mangroves that are gaining, expanding, and 0 are those mangroves that are almost shrinking. They will be lost based on the model. So we are able to select areas that are more resilient. However, this has a cost. We can see that the total area of the climate smart network is larger than the one of the climate naive. And also, we wanted to see if the global prioritization is more efficient for targeting areas that are more resilient to climate change at lower cost compared to a country level prioritization. So what we did, we ran it also at a country level, so all the targets needed to be reached for each country. And we found that, first of all, it's less able to select the most climate smart areas. So the mean value of climate resilience is lower than the previous one. And also at the end, the cost is quite higher. It becomes around 50% of the global mangrove area, where previously it was around 40%. And here I'm showing also another graph that shows the results more country level. So each dot is a country, right? And the dimension of the dot show the mangrove area that is selected in the climate smart solution. So it's not there. So larger dots are those where we select more area. And we are trying to compare the resilience of the climate smart solution in the country with the climate naive solution. And so those dots that are more on the right side of the dot from this perspective, those that are closer to 2 or 1, are those areas that are where we select more climate smart mangroves in the climate smart solution compared to the climate naive. And on the left side is the opposite. And then the dashed line are the mean value for the whole mangrove area. And what we can see is that when we run a global prioritization, we have, as we say, a lower cost. However, there's a lot of difference between the different countries. So there's some countries where we have a lot of mangroves selected, and some others where the selection is much smaller. And actually, there's some where there's no mangrove selected. While if we include the country, we have a higher cost, we need a larger area, but the distribution of the production is more equal between different countries. And the other thing is the country level solution is a bit less climate smart. And we see this also running it for different thresholds. So this is the most climate smart we run, 0.3, but also 0.05. So that's the threshold we use for the climate selection of the climate priority areas I talked about before. It's a bit less costly in the total area selection, and it's also less climate smart, as we see from the vertical lines. And then we wanted to see how does the current network of protected areas compare with the selected climate smart network. And what we found is that, so in general, both including category 4 or category 6, or all the protected areas, we see that our selected priorities were more resilient to climate change. Yes, so wrapping up, our main finding is that climate smart production is not much more expensive. However, this is just for a modest increase in the amount of climate resilience of the network we selected. That the design of climate smart protected areas encompasses a lot of trade-offs. There's trade-offs between the total area that we want to protect, the fact that we are including other features, like we want to develop local scale prioritization, or we want to include diversity, including ecoregion, and this spreading the risk and the amount of climate resilience. So if we want a network that is more climate resilient, it will need to be larger or more costly, frankly. And then we concluded that international collaboration would increase the efficiency of climate smart prioritization, and also the fact that the current network of protected area doesn't really try to maximize climate resilience. So yeah, thank you so much.
Thanks, Alvise. Does anyone have any questions? I have one. So So I see, okay, so you've locked in an area that's climate resilient, so that kind of has to make it more expensive, right? Because you've got this reason that like, you have to include. Is there any scope, and I don't know enough about mangroves, whether or not this is useful, maybe I'm just being a bit mean, but like, could you use it at the other end as well, given that we've got 10 to 15 years of like locked in warming? Could you look at areas and be like, yeah, they're cooked, like the water temperature here is going to be so high that like everything's just going to die.
Yeah.
And just take them out entirely, so that then maybe it, because you know they might be a good area to protect now, but maybe in the future, if you know that that area is going to have no mangroves in it, like if you take it out now, then maybe the solution could be somehow cheaper.
Yeah,
I don't know. Is that really thoughts?
It's like I don't think it will make it cheaper, because then like you will just removing areas and then to try to reach all the targets, you have like more constraint kind of. But yeah, it's like what we were thinking when we were discussing about it. If like we want to both just select the areas, like just include the areas that are more resilient, or also try to remove the areas that are probably going to be lost. So yeah, it's something we're still deciding, because it's not done. It's done.
Yeah. So obviously, yeah, I guess there's things that protected areas can do and can't do. If the ocean is getting warmer, a protected area maybe stop that.
Yeah.
Cool. Any other questions? Yeah,
Of course, I would have a question. What like variables did you use to predict like your climate resilient or your climate smart areas? Was it like
So I didn't run all the model.
I don't know if you mentioned that or not.
It was like Christina that did all of that. But I remember, if I remember correctly, there's for sure there's like droughts, because we are including data from that. I think so. There's extreme precipitations.
Yeah.
There's human barriers. There's sea level rise. There is sediments.
Yeah.
There is.
Yeah. So
There's like cyclone, like winter cyclone.
So like the biophysical, like the climate, like physical, and then that's what I was going to ask, if you were accounting for human barriers.
Yes.
That
Yeah,
accommodation space.
she's including all of
Yeah.
that. But yeah, I can send you the paper. I think it's in green, so it's. Thank you.
Any other questions? Right. Oh, Hugh.
Maybe following up on that, I mean, protection with mangroves is a little bit tricky, isn't it? You sort of alluded to it,
Yes.
but maybe you didn't allude as much to the fact that every country is very different.
Yes.
I think in Malaysia, when we were doing the marine protected areas, they put mangroves in. And mangroves, I think they were protected by national parks, but in other places, they're marine parks, and sometimes marine parks, primary industries. Sometimes, because between high tide and low tide, it's often not even clear who owns it or who has jurisdiction over it. Sometimes it's nobody, sometimes it's everybody. So, that to me it seems to be one of the crucial issues on a country by country basis, how easy it is. And it's bureaucratic complexity more than anything else, isn't it? Yeah. And then the second one, which we talked about most of that paper, is what is the real cost of allowing mangroves to move inland?
Yeah.
And that's a complicated question as well, isn't it?
Yeah, definitely.
But costing that out seems highly problematic, because it's not just buying the land, there's a whole heap of other things. It's not even then clear who owns the land. I think in Australia you can only own down to high tide.
Okay.
So what happens if the high tide goes up? Who owns it?
Yes.
Do you own it? I don't think you do. The state's taking it away from you, maybe. But anyway, I think from a practical perspective, knowing a lot more about the details of what is possible to the country and state, and how much it really would cost to allow mangroves to move in there. Surely that's their future, right? Most of them have to move in there.
Yeah.
At some point rather.
Yes.
2 meters of sea level, 2 meters of sea level rise
Can't really stop.
kills them all, doesn't it?
Yeah, but then I think if you're like you were saying like to exclude some areas, but then you can't really just think of mangroves on their own, because there'll be transitions So those areas that were mangroves, that they could transition into seagrass, for instance. So, and then you should really be thinking about it like just not mangroves exclusively, but rather like, yeah, the coastal wetland ecosystems which occur.
So I don't know, I mean, you've got presumably slopes and land costs and I mean, to really do even with migration, you need a lot of geomorphological data and a lot of social and political data.
Yeah.
I think.
Yeah, I think to make it like practically really practical, yeah, that's something that would be really interesting. Just try to like see how much it will cost, like make it possible for migrating to land.
I'll start.
I just had a question about if you protect the mangroves, does that mean that the ecosystem services in terms of provision would go down in terms of using it for fisheries or
I mean,
timber or any of those things?
yes, I think it depends on like what ecosystem service. Like for example, for fisheries, I don't think, because like it depends like how big is the protected area, definitely. But then most of the species like grow in mangroves but then there's many that can migrate then for reefs or outside and then increase the fishing outside of the protected area. So that's a benefit provided then for sure for the coastal protection if they're connected mangroves. Those would stay there. So yeah, I think it really depends on the ecosystem service, and then it also depends how you're protecting. We're looking to protected areas where indigenous community can still fish, and that's a benefit for them that they're protected.
Yeah, and I guess if it's Indigenous managed, then that might be why it's high biodiversity value and high ecosystem service value, and it may not need those regulatory protections. That might, I don't know, I'm not sure. That might not be the best way to go.
No questions online, but there's compliments from Ant. Well done, nice.
Makes sense. Yes.
Thank you for the question.
Thank you.
Context multiple mangrove species, but do they have high genetic diversity in leaves? So do we need to consider such genetic diversity when selecting priority use?
I think considering genetic diversity, spatial varietization is always probably important, but I'm not sure for mangroves, like I've never really into genetic diversity of different species. However, yeah, it's something we try to do in the paper we did for ecosystem services, including marine province. So we were trying to protect a certain amount of species in each marine province, and the idea is like because they are far wide, probably there's some diversity in species. And it's saying like if you do country level prioritization, you maybe are able to protect some genetic diversity. But yeah, we haven't really got into genetic part.
And most of the other global versions of this that incorporate mangroves or any of these habitats, they don't differentiate between species.
Yeah.
So any differentiation within species is like order of magnitude more refined than we had before. So genetic diversity within those species would be next level.
I mean, yeah, I can partly answer that, but because I mean, you based biodiversity on the plant species, and there's there's over 60 species of mangroves, and the number of plant species, so species richness decreases from the equator to the poles. So, so if you're looking to just look based on biodiversity on plant richness, it's a bit problematic, and I would say it's better to go a multi-diversity approach, because mangroves obviously have a lot of biodiversity for invertebrates and vertebrates. So, but that's really hard to do at a global scale. So I think that's kind of a limit of global analysis to really get that biodiversity, to be able to measure that accurately is different.
I'm just curious about the seaward and landward forecast, if it's correlated to, what's the correlation with the expansion or reduction of mangroves? I remember 10 years ago in Northeast Brazil, where I came from, we had a case where they built like a dam and we had less fresh water into the ocean. And we had a larger area of brackish water. So they were saying, look, the dam it's great because it's expanding the mangroves. So I'm just curious about the correlation of the seaward and landward forecast related to the expansion or reduction of mangroves. Is there any intrinsic correlation?
I mean, I don't think they're correlated. Like they have different like cues that cause the migration landward or seaward, and so they're kind of. That's also why I think Christina made run the model separately. But yeah, I think also the main difference is also on the seaward side. There's going to be much more loss compared to the landward, because on the landward, if there's the possibility, mangroves will be able to migrate if that's possible. There's no barriers. The slope is not too high. There's a possibility for mangroves to migrate on that side. But then I haven't really worked on this part.
I know it's complicated,
So-
but for like global mapping, I'm talking about something local, so it's hard to generalize. Thank you.
I was just wondering what the difference between people protection and property protection were in the ecosystem services.
Yes, yeah, I think they were like, the fact is, in one of the layers was like number of people that were protected from the flooding, and the other was the value of the properties that are protected. So the main difference was like in really, let's say, which city, maybe the value was really high, but the number of people was not that high, but maybe there's some other cities in developed countries where like you have a really high number of people, and but then the total value on like the buildings is lower. So that's we try to look for it.
Just a comment, I just wanted to thank Alvise who jumped in at the last minute to do this presentation, which is also a call for everybody. I think in trying to drum up some business, Kate, we got seminars all the way through August, is that correct? But after August, we have a lot of openings, so thank you, Alvise, very much for being willing to do this, and it's actually quite amazing that you've been a PhD student for 6 months now, and you're having all the results for that second suite of work as well, so thank you.